in order to get into quantum mechanics, we have to take a little side trip to physics and learn a little bit about light and electromagnetic radiation. Because the interaction of light with atoms helped to shape the scientists' models of the atom. It was a very important experiments and the observations from them. So light is a form of electromagnetic radiation. So electromagnetic, there's an electric field and a magnetic field, and it's a form of energy. Light is not matter. It does not occupy space and have mass. Light is important, but it is not a form of matter. Light is a type of energy that travels through space at a constant speed of 3 times 10 to the 8th meters per second. And just in miles per second, to give you a number that you can relate to, light travels 186,000 miles in 1 second. It's really fast. And we call that speed the speed of light. So all light travels at the speed of light. Light has properties of both waves and particles. So the wave business makes a lot of sense, but sometimes light acts as a particle, and that's where we get into the quantum mechanics, and that's where it's disturbing. So here we have a photograph of water droplets hitting a still surface of the water. And we know from just being alive and seeing stuff that when the water droplets hit the surface of the water, they cause ripples, right? Little tiny waves, and those waves move away from the point of impact in concentric circles. And they go out, and they just get smaller and smaller, and they disappear. Those waves are carrying energy. When the droplets hit, they have kinetic energy. And that kinetic energy goes somewhere, it goes into the wave, and the wave carries energy as it moves through the water. If you've ever been to the coast and stood in the surf, as waves come and crash on you, you know that waves carry energy. They can knock you flat, right? So water has waves, and thinking about the waves of water can help us to understand the wave nature of light. We can see the light, but we can't see how it's being a wave. So a wave is going to have this shape. It's actually a sine function if you're interested in that. And we can measure a couple of different things about the wave. We can measure the distance from one peak to the next peak. That's called the wavelength. It's the length of a wave. And that's given the symbol lambda. That's a Greek letter L. It looks like an upside down Y. How long the wave is determines the color of the light. You change how long the wavelength is, and the color that we perceive is going to be different. So here are the waves traveling in this direction. How fast is it going? The speed of light. Light travels at the speed of light. There's a question on a pre-lab for experiment 7. I'm trying to give you guys some hints to see if I can, because most people screw that one up. Light travels at the speed of light. So white light has a whole bunch of different wavelengths. Yeah, question?
Can you slow down light though?
Can you slow down light? I think that is possible, but it takes a lot of doing. Yeah, you can get into, ideas of relativity, which Einstein was also involved with. Personally, that sort of stuff makes my head hurt, but physics people like that. So white light has a whole bunch of different wavelengths in it. And if you take white light, like from an incandescent light bulb, pass it through a slit and through a prism, you can separate it into a rainbow of colors. All of these colors were present in the light that came from this light bulb. As the light goes through the prism and the refractive index of the air outside and the material that the prism is made of causes the wave to bend, it's going to bend a little differently depending on its wavelength, and that's what separates it. That's all physics. Okay? And the order of the colors is always the same. It goes from red on one side to violet on the other. Color is really, yeah, question?
Just to make sure, you're talking about a tangible prism, not some other abstract.
Yeah, I'm talking here about a tangible prism. You can make them out of plastic or glass, and it's the same thing that happens in a rainbow. Rainbow, the droplets of water in the air are acting as prisms and causing the light to be separated. It's really pretty neat. There are a lot of things in our everyday lives that we generally just go around and we don't even think about it. And then you start to think about it and you're like, oh my goodness. So her shirt is red. Why? Why is her shirt red? How can I tell that her shirt is red? How does that work? That can just kind of rock your boat a little bit. What the heck? Well, physics can actually explain that. Her shirt is red because as sunlight comes in, sunlight contains all the colors. Her shirt is absorbing most of the colors and reflecting the red color. And so the red light bounces off her shirt and comes to our eyes, causes a rearrangement in some molecules in the back of our eyeballs, which our brain interprets as a pretty red color. Anybody have any questions? What if you're colorblind? Yeah. So the way that your brain interprets, and there's rods and cones, and you can have missing colors and stuff. If you're colorblind, and usually colorblind does not mean that you see the world in black and white. It means that there's a distortion in your perception of color. 4 of my 5 sons have some color blindness, a red-green issue. And what happens is colors that are kind of muddy in between, like sometimes you'll argue with a friend over, well, is that blue-green or green-blue, right? So there are some colors in the middle there that they would say are different than what I would say. Like navy blue, several of them would tell me is purple. Because their brain sees it differently. Because there's a defect in how their eye interprets the color. They cannot tell the difference between some things. One of my sons can't see red paper clips in green grass.
My husband's colorblind and the green grass looks orange to him.
Yeah. My uncle is colorblind, and he said in the spring the grass was the same color as the fire truck. But later in the summer, it wasn't. They were different colors. Because, new grass is a slightly yellower color. It's a brighter color than grass that's been there for a while. It was really interesting. Yeah. It's the whole aspect of color vision. And, so then you're like, well, maybe that's why some people like red and some people don't like red. Some people think yellow's a horrible color. Other people like yellow. Well, maybe it looks really different to them. Yeah. Then you're like, can I even prove that anything is... Yeah. You can really give yourself a headache. And then you just have to say stop, and we'll go on to the next topic here. We'll talk about frequency. So frequency is given the symbol nu, which is sort of a curvy V, which is really unfortunate because V is velocity and frequency is nu, and they are very easily confused. Sorry about that. I was not in charge of that. So frequency is the number of cycles or crests of the wave that pass through a stationary point in 1 second. Frequency and wavelength are inversely related. If you have a long wavelength, you will have a short frequency, a small frequency. If you have a short wavelength, you'll have a high frequency. So I'm going to draw some ugly pictures. Okay, so here's a person. That's why I'm not an artist. And let's think about let's look at a couple of waves. So here we have one wave, and here we have another wave. Which wave is going faster? They're going the same speed. The speed of light.
Speed of light is the speed of light.
The speed of light is the speed of all light. Okay? I know, it's hard. This one looks like it's going faster, though, doesn't it? It looks like it's just bouncing all over the place. This one has more energy, but it's traveling at the same speed. So it moves at the same speed as this one. But if you're this person and you're counting, say, I'm going to count wave crests for a minute or a second or whatever unit of time. This one is going to have more crests that pass in that same amount of time than this one, right?
So could frequency determine the intensity of light then? How you perceive it?
Intensity is actually the amplitude, how high the wave is from crest to trough. Okay? And because that doesn't come into our discussion, I don't usually mention it. But yeah, the brightness of the light would have to do with the amplitude of the wave. So the speed's always the same. Frequency and wavelength are inversely related. So this one, if we look at its wavelength, right? Here's the wavelength. And on this one, the wavelength is here. Here, this one has a longer wave, and this is a shorter wave. But this is more passing per second than this one. So this is short wavelength, high frequency. And this is long wavelength, low frequency. And the unit on frequency is cycles per second, or often just per second, whatever's per second, waves per second. Okay? So light is energy. It has a wave nature, but light can also be viewed as a stream of particles. And the name for a particle of light is a photon. So a photon is a particle of light or a single packet of light energy, a piece of energy. That's kind of a strange concept, like a piece of milk. How do you have a piece of milk? What? How do you have a piece of energy? Well, it's a photon. It is a piece of energy. How much energy is carried in that packet depends on the wavelength. Shorter wavelength, greater energy. Light waves carry more energy if their crests are closer together. That's high frequency, shorter wavelength. So if we go back to my picture and we look at these, this one looks more energetic, doesn't it? This looks like a hyper kid jumping up and down. And this is like slow, right? This is low energy, this is high energy. So this is high energy and low energy. And there will be questions where you have to relate these things. And this is how I recommend that you do it. Draw yourself a little picture. One that's going up and down, very short wavelength, one that's really slow looking. They all travel at the same speed though. This is low energy, that's high energy. You can see the wavelength. This is short, this is long. And if you imagine these traveling past you, you can get the frequency, whether it's high or low. Okay, we're not really going to do calculations so much, but we need to understand high energy, high frequency, low wavelength, short wavelength. Okay?